You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The journey of artificial intelligence begins with data, and the preparation of that data is perhaps the most critical stage in the entire process. Algorithms, no matter how sophisticated, cannot function effectively without clean, structured, and carefully validated information. Raw data often arrives in a form that is incomplete, inconsistent, or riddled with errors. Left untreated, these flaws can lead models to learn patterns that reflect noise rather than truth, producing inaccurate or even harmful outputs. Preparing data involves a series of deliberate steps: cleaning errors, structuring information, validating entries, and ensuring consistency across variables. This work is often invisible compared to the glamour of advanced models, but it is indispensable. A poorly prepared dataset can sabotage even the most powerful architecture, while well-prepared data can allow relatively simple models to achieve remarkable results. For learners, this stage emphasizes that AI success depends as much on disciplined data practices as on innovative algorithms. Data for AI systems can come from many different sources, each offering unique benefits and presenting distinct challenges. Sensors attached to devices like cameras, microphones, and GPS units capture streams of observations about the physical world. Digital transactions, whether from banking, e-commerce, or healthcare systems, produce highly structured logs that detail interactions with precision. Web activity creates clickstreams, search histories, and browsing behavior records, while publicly available datasets offer open resources for research and experimentation. Scientific instruments generate specialized data, from genomic sequences to climate readings, that feed into domain-specific AI applications. Yet not all sources are equally reliable or sufficient for the task at hand. Sensor data can be noisy or incomplete, transactional records can reflect only narrow perspectives, and public datasets may not match the exact context of a project. Recognizing the strengths and weaknesses of each source ensures that data collection strategies align with the intended application, balancing richness, precision, and relevance. The methods of acquiring data are as diverse as the sources themselves. Surveys and questionnaires capture direct human input, collecting preferences, attitudes, or experiences. These methods provide valuable subjective insights, but risk introducing bias if questions are poorly designed. Web scraping automates the collection of content from websites, transforming unstructured pages into structured datasets, though this approach must navigate ethical and legal considerations. Application Programming Interfaces, or APIs, allow structured access to information from online services, offering efficiency and consistency but depending on the reliability of third parties. Direct measurement through sensors, IoT devices, or lab equipment provides continuous streams of real-world observations but requires careful calibration and maintenance. Each method balances trade-offs: cost versus scale, precision versus representativeness, accessibility versus ethical boundaries. For learners, understanding acquisition methods reinforces that data does not simply appear ready for analysis. It must be thoughtfully gathered with attention to both technical and societal implications. Ethics must be woven into data collection from the very start. Gathering data without informed consent, mishandling sensitive information, or reinforcing unfair patterns can undermine not only the integrity of AI systems but also the trust of the societies they serve. Privacy protection requires that personally identifiable information be secured or anonymized to prevent misuse. Consent means individuals understand how their data will be used and have agreed to participate willingly. Fairness demands that datasets represent diverse populations rather than overemphasizing one group at the expense of others. For example, if an AI system for healthcare relies on a dataset that underrepresents certain ethnic groups, its predictions may perform poorly for those patients, deepening inequality rather than alleviating it. Ethical collection is not just about complying with regulations like GDPR or HIPAA, it is about respecting the dignity and rights of individuals. For learners, this emphasizes that ethical discipline is inseparable from technical rigor. Structured data preparation focuses on formatting information into rows, columns, and tables that can be processed effectively by algorithms. In this form, each row typically represents a single observation, such as a patient record or a sales transaction, while each column represents an attribute, like age, date, or purchase amount. Preparation of structured data often involves ensuring that categories are consistently labeled, numerical values are standardized into common units, and dates follow uniform formats. For example, a data set that mixes the 2nd of January 2023 with February 1, 2023 risks confusing algorithms that rely on precise formatting. Even seemingly trivial inconsistencies can derail analysis. Structured preparation is often deceptively complex. While the format appears neat, the underlying data may still contain contradictions, duplications, or inaccuracies. This stage demonstrates that the orderliness of tables is not automatic. It must be imposed deliberately through careful checking and reformatting. Unstructured data requires entirely different preparation techniques because it does not naturally fit into tabular rows and columns. Text documents, images, audio files, and videos are all examples of unstructured data. Preparing text may involve tokenization, the removal of stop words, and the conversion of characters into machine-readable embeddings. Images often need resizing, normalization, or annotation to highlight objects of interest. Audio data might be transformed into spectrograms, representing sound waves as visual features, while video data must be divided into frames or segmented into meaningful sequences. Unstructured data presents the majority of human communication and observation, but it also carries more complexity and variability. The task of preparation is to translate this richness into forms that algorithms can analyze without losing essential meaning. For learners, this stage shows how AI systems bridge the sensory world of humans with the structured logic of computation. Cleaning data is a painstaking but essential process that removes errors, inconsistencies, and noise from datasets. Duplicates must be identified and eliminated so they do not skew results. Obvious errors, such as impossible values for age or location, must be corrected or removed. Categories must be standardized so that NY, New York, and NY are not misclassified as separate entities. Outliers must be investigated to determine whether they represent genuine anomalies worth preserving or mistakes that distort patterns. Data cleaning is often iterative, revealing new issues as the dataset is examined more closely. It is sometimes estimated that up to 80% of a data scientist's time is spent cleaning rather than modeling. This statistic reflects the reality that messy inputs cannot produce reliable outputs. Cleaning ensures that what remains is trustworthy, turning chaotic raw material into the kind of data that supports meaningful learning. Missing values are among the most common issues in real-world datasets. Rarely is every attribute recorded perfectly for every observation. Handling these gaps requires thoughtful strategies. Imputation involves replacing missing values with estimates, such as the mean or median of available data, or predictions from related variables. Interpolation can fill gaps in time series data by estimating values between known points. Sometimes the best approach is exclusion, removing rows or columns with excessive missingness to preserve dataset integrity. Each strategy has trade-offs. Imputation risks introducing bias. Interpolation may mask variability, and exclusion reduces the dataset size. The goal is to minimize distortion while maintaining utility. For example, in healthcare datasets, missing lab values might be estimated based on patient history, but for critical measures, exclusion might be safer. Handling missing values underscores that preparation is not mechanical. It requires judgment about which imperfections to address and how. Normalization and standardization ensure that features measured on different scales are made comparable. Without these adjustments, algorithms may overemphasize features with larger raw values. Consider a dataset with two variables, one measuring income in dollars and another measuring age in years. If left unscaled, The income feature, with values in the tens of thousands, could dominate the model, overshadowing the influence of age. Normalization rescales features into a common range, such as 0 to 1, while standardization transforms them into values with a mean of 0 and a standard deviation of 1. These processes prevent arbitrary differences in measurement from distorting patterns. For learners, normalization and standardization illustrate how technical details of preparation can fundamentally shape model behavior, ensuring that insights reflect genuine relationships rather than quirks of scale. Feature engineering is the art of designing attributes that capture meaningful relationships in data. Rather than relying on raw inputs, practitioners transform or combine variables to create features that highlight relevant patterns. For example, in financial modeling, debt and income can be combined into a debt-to-income ratio, a feature that better predicts creditworthiness than either value alone. In text analysis, features might include counts of specific terms or sentiment scores derived from language. Feature engineering requires domain expertise, creativity, and experimentation, and it often distinguishes mediocre models from excellent ones. Even in the age of deep learning, where models automatically learn features from raw data, human-driven feature design remains important in many contexts. For learners, this practice emphasizes that algorithms are not omniscient. They depend on thoughtfully prepared inputs to succeed. Encoding categorical data ensures that non-numeric information can be processed by algorithms. Categories like red, blue, and green cannot be used directly without translation into numerical formats. One-hot encoding creates a binary variable for each category, marking presence or absence, while ordinal encoding assigns numbers to categories that have a natural order, such as low, medium, and high. Choosing the right encoding method matters because algorithms interpret numbers differently. Treating unordered categories as ordinal, for instance, could mislead a model into assuming relationships that do not exist. Encoding highlights the subtlety of preparation decisions. A simple choice about representation can have dramatic consequences for how a model interprets the world. For learners, encoding demonstrates that machine learning requires both technical and contextual understanding to convert categories into usable, meaningful features. Balancing datasets is necessary when training models that rely on fair representation across different classes. In many real-world problems, one class dominates the data, creating an imbalance that biases predictions. Fraud detection is a classic example. Fraudulent transactions are rare compared to legitimate ones. A model trained on such data might achieve high accuracy by predicting legitimate for everything, but it would fail at its true purpose detecting fraud. Balancing strategies include oversampling the minority class, undersampling the majority class, or generating synthetic examples using techniques like SMOT. The aim is not to distort the dataset, but to ensure that models are forced to consider all classes equitably. For learners, dataset balancing reveals how preparation decisions shape not only accuracy but also fairness, influencing whether AI systems serve all users effectively. Splitting data into training, validation, and test sets is a cornerstone of reliable AI development. The training set is used to teach the model, the validation set helps fine-tune hyperparameters and prevent overfitting, and the test set provides a final evaluation of performance on unseen data. Without proper splitting, models risk memorizing patterns rather than learning generalizable relationships. For example, testing a model on the same data it was trained on might suggest excellent accuracy, but in practice the system would falter when faced with new inputs. Partitioning datasets ensures that evaluation reflects reality, grounding performance metrics in genuine adaptability. For learners, this practice illustrates that preparation extends beyond cleaning and formatting. It also includes structuring data responsibly to test whether models will succeed outside controlled training conditions. Data documentation provides the transparency needed to use datasets responsibly and reproducibly. Metadata describes when, where, and how data was collected, while data dictionaries define the meaning of variables and categories. Lineage tracking follows how data changes over time, recording cleaning steps, transformations, and updates. Documentation prevents misuse by clarifying the scope and limitations of datasets. For example, a dataset may appear comprehensive but actually represent only one region or demographic group. Without proper documentation, such limitations might be overlooked, leading to biased models. For learners, documentation emphasizes that datasets are not just collections of numbers, but complex resources with history and context. Clear records allow others to verify results, replicate experiments, and understand the boundaries within which conclusions can be trusted. Common pitfalls in data collection and preparation can undermine even the most ambitious AI projects. Sampling bias occurs when datasets are not representative of the broader population, leading to skewed predictions. Measurement errors from faulty sensors, inconsistent logging, or human mistakes can introduce noise that confuses algorithms. Data leakage, where information from test sets inadvertently influences training, can create inflated performance metrics that collapse in real-world use. These pitfalls demonstrate that data handling is not neutral. It requires active vigilance and discipline. For learners, understanding these risks reinforces that preparation is as much about avoiding harm as it is about enabling performance. Missteps in collection or preparation can cascade into flawed models, making awareness of these dangers essential for anyone building or evaluating AI systems. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Automation in data preparation has become increasingly important as datasets grow larger and more complex. Manually cleaning, formatting, and validating millions of records is impractical, so automated pipelines are designed to handle repetitive tasks consistently and efficiently. These pipelines can remove duplicates, flag outliers, normalize values, and apply transformations at scale, all while logging each step for transparency. Automation reduces human error, ensures reproducibility, and frees practitioners to focus on higher-level analysis rather than tedious chores. For example, in e-commerce, automated scripts can continuously clean and categorize new product listings, ensuring that models always train on up-to-date information. The rise of automation also introduces challenges, such as ensuring that automated processes themselves are correct and adaptable. For learners, automation illustrates the balance between efficiency and oversight. While machines can streamline preparation, humans must still design, monitor, and refine these systems to maintain reliability and fairness. Data augmentation provides another way to strengthen datasets, especially when real-world data is limited or expensive to collect. Augmentation creates synthetic variations of existing samples to increase diversity without altering fundamental meaning. In image analysis, techniques include flipping, rotating, cropping, or altering brightness to simulate different viewing conditions. In text, augmentation may involve paraphrasing or substituting synonyms, while in audio, it can include shifting pitch or adding background noise. These variations help models generalize better, reducing the risk of overfitting to narrow datasets. For example, a medical imaging system trained only on pristine scans may fail on real-world data with slight distortions, but augmentation can prepare it for such variability. Augmentation shows that preparation is not just about cleaning data, it is also about enriching it. For learners, this highlights how thoughtful design can transform limited datasets into robust foundations for training reliable AI systems. Labeling strategies are central to supervised learning, where models learn by associating inputs with known outputs. Labels provide the ground truth against which predictions are compared, guiding the adjustment of model parameters. In computer vision, this might involve annotating images with bounding boxes around objects. In language tasks, it may mean tagging words with parts of speech or sentiment. Labeling can be simple for small datasets, but becomes labor-intensive as scale increases. Poor quality labels introduce noise that confuses models, while consistent, accurate labels enhance performance dramatically. Approaches vary from manual expert labeling to semi-automated methods supported by annotation tools. For learners, labeling demonstrates the collaborative nature of AI development. While algorithms perform the learning, humans often supply the structure and correctness that make effective learning possible. Labels embody the connection between raw data and meaningful outcomes. Human-in-the-loop labeling acknowledges that human expertise remains vital even in the age of automation. Crowdsourcing platforms allow large groups of people to annotate data quickly, producing scale at relatively low cost. However, tasks requiring precision, such as labeling medical scans or legal documents, demand domain experts. Expert review ensures that annotations are both accurate and contextually valid. In many workflows, humans validate or correct machine-generated labels, combining efficiency with oversight. For example, a speech recognition system might auto-transcribe audio, but humans refine the transcripts to ensure quality. This iterative partnership accelerates dataset creation while maintaining standards. For learners, human-in-the-loop systems show that AI is not a replacement for human intelligence, but an amplifier of it, leveraging collaboration to produce high-quality labeled data that underpins trustworthy models. Semi-supervised labeling bridges the gap between scarce labeled data and abundant unlabeled data. In this approach, a small set of labeled examples trains a model, which then assigns provisional labels to the larger unlabeled set. Human review or additional algorithms refine these labels, gradually expanding the dataset's reliability. This approach is particularly valuable when labels are costly or time-consuming to obtain. For example, in medical AI, where expert annotation is expensive, semi-supervised methods allow systems to leverage vast quantities of unlabeled patient data while minimizing reliance on scarce expert time. Semi-supervised learning shows how creativity and preparation can unlock value from imperfect resources, ensuring that progress is not stalled by labeling bottlenecks. For learners, it illustrates how efficiency and ingenuity are as crucial in AI as raw data volume or computational power. Active learning takes the principle of efficiency further by having models select the most informative samples for labeling. Instead of labeling every data point, systems identify those that would most improve performance if clarified. For example, a language model might struggle with sentences containing unusual idioms and flag them for human annotation. By focusing human effort where it matters most, active learning accelerates dataset improvement while reducing labor. This method reflects a strategic use of resources. Not all data points are equally valuable for learning. Active learning illustrates how AI systems can collaborate with humans in refining their own training process. For learners, it shows that preparation is not only about volume but also about prioritization, emphasizing that quality and relevance of data matter more than sheer size. Data wrangling tools play a practical role in preparation, offering frameworks for cleaning, transforming, and integrating datasets. Libraries like Pandas in Python simplify the handling of structured data, enabling filtering, aggregation, and reshaping operations with minimal code. SQL provides powerful querying capabilities for databases, while specialized tools support large-scale distributed processing. These tools make complex preparation tasks manageable, standardizing workflows, and improving reproducibility. They also democratize data preparation, allowing practitioners without deep programming expertise to engage with datasets effectively. For learners, mastering data wrangling tools is essential as they form the day-to-day toolkit of AI development. Just as carpenters need hammers and saws, data scientists rely on wrangling frameworks to shape raw material into usable form. Tools illustrate how preparation, though conceptually challenging, is made feasible through practical and accessible infrastructure. Cloud services have transformed data preparation pipelines by providing scalable, flexible environments for ingestion, cleaning, and transformation. Platforms like AWS, Google Cloud, and Azure offer data lakes, ETL pipelines, and automated preprocessing frameworks that can handle terabytes or petabytes of data. These services enable teams to collaborate globally, accessing shared datasets and workflows from anywhere. They also integrate security, compliance, and monitoring tools, addressing the complexities of responsible data handling at scale. Cloud-based preparation supports continuous pipelines, where new data flows seamlessly into training environments in near real time. For learners, cloud services highlight the shift from local, manual workflows to distributed, automated systems. They represent how infrastructure adapts to the demands of modern AI, ensuring that preparation can keep pace with the size and velocity of contemporary datasets. Data versioning ensures that datasets remain reproducible and traceable as they evolve. Just as software developers track code changes, data scientists track updates to datasets, including modifications, additions, and preprocessing steps. Versioning allows researchers to recreate past experiments, ensuring that results can be verified and compared. It also prevents confusion when multiple teams work on the same dataset, providing clear records of what was used when. Tools for dataset versioning store snapshots and document transformations, creating a lineage that supports transparency. Without versioning, AI projects risk inconsistency, with models trained on slightly different data producing conflicting outcomes. For learners, data versioning demonstrates that preparation is not static. It is dynamic and iterative, requiring systems that preserve accountability while supporting progress. Data privacy techniques are essential for protecting sensitive information during preparation. Anonymization removes personally identifiable details, pseudonymization replaces them with coded identifiers, and encryption secures data both at rest and in transit. These methods reduce the risk of exposing individual identities while preserving the utility of datasets for analysis. For example, medical records may be stripped of names and addresses, but still retain diagnostic codes useful for training models. Privacy techniques must balance protection with utility, ensuring that datasets remain meaningful while respecting individual rights. For learners, privacy illustrates that preparation is not just technical, it is ethical and legal, demanding awareness of how data is handled at every stage. Responsible preparation requires embedding privacy safeguards directly into workflows, not as afterthoughts. Compliance in data handling reflects the legal frameworks that govern collection, preparation, and use. Regulations like the European Union's General Data Protection Regulation and the United States Health Insurance Portability and Accountability Act impose strict requirements on how data is stored, processed, and shared. Non-compliance can lead to legal penalties, reputational harm, and loss of trust. Compliance demands not only technical measures like encryption, but also organizational policies, audit trails, and accountability structures. For example, GDPR mandates the right to be forgotten, requiring systems to allow deletion of personal data upon request. For learners, compliance emphasizes that AI operates within social contracts and legal boundaries. Data preparation must therefore align not only with technical goals, but also with the ethical and legal responsibilities of the societies it serves. Quality metrics provide a way to evaluate datasets systematically, ensuring they are fit for purpose. Completeness measures whether all necessary attributes are present, while accuracy assesses whether values reflect reality. Consistency checks whether values align across records, and timeliness evaluates whether data is current. These metrics provide quantitative indicators of readiness, guiding decisions about whether further cleaning or augmentation is required. For instance, a financial dataset with missing transaction dates may score poorly on completeness, undermining its utility for fraud detection. Quality metrics make data preparation measurable and transparent, transforming what might otherwise seem subjective into accountable standards. For learners, metrics demonstrate how preparation is evaluated rigorously, ensuring that datasets provide a reliable foundation for training models. Bias detection is a critical part of dataset evaluation, ensuring that hidden imbalances do not undermine fairness. Techniques include statistical analysis to check whether categories are underrepresented, adversarial testing to reveal blind spots, and visualization tools to highlight disparities. For example, a facial recognition dataset might disproportionately include lighter-skinned individuals, leading to higher accuracy for one group than another. Detecting such biases allows practitioners to take corrective steps, such as augmenting the dataset or adjusting algorithms. Bias detection is not about perfection but about awareness and mitigation. For learners, it highlights that preparation shapes not only technical performance but also ethical outcomes. Models inherit the qualities of their data, so ensuring balance and fairness begins at the preparation stage, long before deployment. Continuous data collection reflects the shift toward pipelines that update datasets in real time. Rather than static snapshots, modern AI often depends on streams of new data flowing into training and evaluation environments. This approach ensures that models remain relevant as conditions change, such as adapting to evolving consumer behavior, shifting language use, or emerging security threats. Continuous pipelines require infrastructure for ingestion, cleaning, and validation that operates automatically, often in cloud-based systems. For example, recommendation engines update daily or even hourly, integrating the latest interactions to refine suggestions. Continuous collection ensures adaptability, but also introduces challenges in maintaining consistency and preventing drift. For learners, it demonstrates that preparation is not a one-time event but an ongoing process, reflecting the dynamic nature of the real world. Ultimately, data preparation is the foundation upon which all AI performance rests. Well-prepared data ensures that models learn meaningful patterns, make fair predictions, and adapt effectively to new scenarios. Poor preparation guarantees failure no matter how advanced the algorithms. Preparation encompasses technical precision, ethical responsibility, and organizational discipline, making it one of the most interdisciplinary aspects of AI. It transforms raw, messy inputs into reliable, structured resources that can support robust, transparent, and trustworthy models. For learners, the lesson is clear. Data preparation is not a background task to be rushed, but the central stage upon which the success of AI depends. It is here that accuracy, fairness, and responsibility are first established, long before models produce their outputs. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.